Hi friends, welcome back to another video. So today I'll be explaining physics May-June 2014 paper 31. Question 1a states figure 1.1 shows a liquid in glass thermometer. Part 1 states in the process of making the thermometer the scale division was spaced equally. What assumption was made about the liquid? Liquid has a uniform expansion. So this will be the final answer. Then suggest part 2 states suggest two changes to the thermometer that would require the spacing of the scale division to be larger. First is use liquid with greater expansion and second is use narrow capillary tube. Then part 3 states as a result of changes in part 2 what other changes need to enable the thermometer to be used for the same temperature range. A thermometer must be longer. So this is because if the thermometer is longer, it will be easy to read the temperature from the thermometer. Then question B states expression of the liquid is an example of physical property that may be used to measure temperature. State two other physical properties that may also be used to measure temperature. So the first is the color of the metal and second is the pressure of the gas, and also for the third one we can write the expansion of the solid. So you can write either the color of the metal or the pressure of the gas or the expansion of the solid. So this is three other physical properties that you may write to measure the temperature. Question 2 states a student has a large number of coins of different diameters, all made of the same metal. She wishes to find the density of the metal by a method involving placing the coins in water. Part A state the formula needed to calculate the density. So the formula is D is equal to m divided by V, which is mass divided by volume. Then Part B states describe how the measurement of the required quantities are carried out. Pour some water in the measuring cylinder and read the initial volume of the water, say V1. Then place the coins in the water and read new level of water in the cylinder, say V2. Then subtract the V1 from V2 to get the volume of the coin, which is V. The mass of the coin can be measured with the help of the top bend balance. So this is how we will calculate the measurement required quantities to be carried out. Then question E states state one precaution taken when carrying out a measurement in B to ensure that the result is as accurate as possible. So the top band balance must read 0. Place eye level with surface in measuring cylinder to avoid parallax error. And then the third one can be read measuring cylinder level at bottom of the meniscus, not at the top of the meniscus. So these are the three precautions that we can take in carrying out the measurement in B to ensure the results are accurate as possible. So these are three and you can write any of these. Question 3A states on a day with no wind, the fountain in Switzerland propels 30,000 kg of water per minute to a height of 140 meters. Calculate the power used in raising the water. So first the formula of calculating the power is P is equal to work done divided by time. So the work done is 30,000 kg multiplied by time, which is the gravitational force multiplied by the height, which is 140. So this is, we will write 30,000 multiplied by 10 multiplied by 140 divided by 1 minute. Per minute is 60 seconds, so divided by 60. Then using this 300,000 multiplied by 140 divided by 60 is 700,000 watts. So we write this in standard form and by writing 7 multiplied by 10 to the power of, there are 1, 2, 3, 4 and 5 zeros, so 10 to the power of 5 watts. Then question B states the efficiency of the pump which operates the fountain is 70%. Calculate the power supplied to the pump. So the efficiency of the pump is 70%. So we write efficiency is equal to output divided by input multiplied by 100. So we have to calculate the power supply, which is the input. So input is equal to output divided by efficiency multiplied by 100. Out here multiply by 100. So here 7 times 10 to the power of 5, which we calculated in the first question, multiplied by 100 divided by efficiency, which is 70%. So the power is 1.0 multiplied by 10 to the power of 6 W or watts. Then question C states, on another day a horizontal wind is blowing. The water table rises vertically. Explain why the water still rises to the height of 140 meters. So the correct answer is the horizontal wind has no effect on potential energy gain. We consider the vertical height of the water. So in this question states why it still rises to the height of 140, because as the horizontal wind has no effect on PE, potential energy gain, we consider vertical height of the water. Question 4 states figure 4.1 shows a heavy ball B of weight W suspended from a fixed beam by two ropes P and Q. So this is a beam with two ropes P and Q, and the weight is pulling these both ropes. Then P and Q are both at the angle of 45 degrees to the horizontal. The tension in P and Q are each 30 newtons. So part A states in the spaces below draw a scale diagram to find the resistance resultant of the tension of in P and Q. Use a scale of 1 centimeter to represent 5 newtons. Label the force and show the direction in which in with arrows. So we will mark this W over here, and then we will draw a 30 newton strength on the right side and 30 newton strength on the left side, which is 30 divided by 5, 6 centimeters. So this will be 6 centimeter and this will be 6 centimeter. Then we will connect these both on the top with using a compass with drawing an R, and then after this we will put a point here and connect these both dots with a line, and then we will measure the length from this to from this point to the diagonal over here, and the length over here will be 8.4 centimeters. So we multiply 8.4 by 5, which will be 42 newtons. So the resultant force is 42 newtons. And then question B states state the direction of the resultant force. So the direction of the resultant force is vertically upwards. Over here it's vertically upwards. Over here we have shown in it must be upwards. It must be upwards over here, but over here it's going towards the top right. So it's vertically upwards. Then the state the magnitude of the W, which is W is 42 newtons. Question 5a states water tank has a rectangular base of dimension 1.5 meters by 1.2 meters and contains 1440 kg of water. Calculate the weight of the water. So we have the dimension and we have the container, and that has the mass, which is 1440 kg. So we'll use the weight of the water is W is equal to mg. So 1440 multiplied by 10 is 14,400 newtons, which will be the weight, final weight, and we'll write this as our final answer. Then part 2 states calculate the pressure exerted by the water on the base of the tank. So pressure is equal to force divided by area, and the force is which is 14,400 newtons divided by the area, which is they have already given us the values, which is dimension is 1.5 meters by 1.2 meters. So we will write 1.5 meters multiplied by 1.2 meter, which will be over here 8,000 pascals. So pressure is 8,000 pascals. Then part B states figure 5.1 shows two water tanks P and Q of different shape. Both tanks are circular when viewed from above. The tanks each contain the same volume of water. The depth of the water in both tanks is 1.4 meters. So over here we have two tanks with the height of water is in which the height of the water is 1.4 meters. Then question 1 states part 1 states the density of the water is 1000 kgs per meter cube. The pressure exerted by the water on the base of the two tanks are equal. Calculate this pressure. So pressure is equal to density times gravitational force multiplied by height, in which the density is 1000 kg per meter cube multiplied by 10 multiplied by the height, which is over here 1.4 meters. So the pressure is 14,000 pascals. Then part 2 states equal small volume of water are removed from each tank. State which tank P or Q now has the greater water pressure on its base. Explain your answer. So the pressure on the base of P is smaller and Q is greater because with same volume removed there is a small decrease in tank Q, small decrease in pressure in tank Q as compared to tank P, because over here the tank Q has small area exerted on the surface of the base, so more pressure will be exerted over here as compared to in tank B, because the area is spread across the surface. So this is how the pressure on the base of B is smaller as compared to Q, and Q is greater because with same volume removed there will be a small decrease in tank Q as compared to tank B. Question 6 states figure 6.1 shows a quantity of gas in a cylinder fitted with a piston P. Describe the motion of the molecules of the gas. So the molecules of the gas move randomly. They move in zigzag motion in all directions. They move very fast at higher speed. They collide with each other. Molecules change direction in collision. Molecules collide with the walls of the container. So this is the answer for question 8, which states describe the motion of the molecules of the gas. Then question B states the piston is now slowly pushed down to decrease the volume of the gas. The temperature of the gas does not change. So part 1 states state and explain in terms of molecules what happens to the pressure of the gas. So the pressure of the gas increases because molecules collide with wall more often and cause more pressure. Since the area in which the gas is fitted uh, is decreasing, the area is decreasing, so the gas molecules will hit the wall of the cylinder more often, and this will create more pressure in the gas cylinder when the piston P is pushed down. So this is what we will write in part 1. Then part 2 states before pushing the piston down, the pressure of the gas was 1 multiplied by 10 to the power of 5 pistons Pascal. Pushing the piston down reduces the volume of the gas from 500 centimeter cube to 240 centimeter cube. So calculate the final pressure of the gas. So the formula is P1 multiplied by V1 is equal to P2 multiplied by V2. So 1 multiplied by 10 to the power of 5 multiplied by 500 is equal to P2 multiplied by 240. So we have to calculate the pressure after pressure at the end when the piston is moved down. So P2 is equal to 1 multiplied by 10 to the power of 5 multiplied by 500 divided by 240. So the pressure created is 2.1 multiplied by 10 to the power of 5 pascals. So this is what we will write in question 2. Question 7 states the following are 3 statements about boiling. First is a liquid boils at a fixed temperature. Second is during boiling, vapor can form at any point within the liquid. Third is without a supply of thermal energy, boiling stops. So complete the following equivalent statements about evaporation. So first is a liquid evaporates at any temperature below boiling point for the first statement. Then the second statement is during evaporation, vapors form at the surface of the liquid. And third is without a supply of thermal energy, evaporation continues, but it is slower. So this is the answers that we will write in 3 the statement, three of the following statements. Then question B states a pan containing water boiling at 100 degrees Celsius is standing on an electrically heated hot plate. In 20 minutes, 0.075 kg of water is lost as steam. The specific latent heat of vaporization of water is 2.25 multiplied by 10 to the power of 6 joules per kilogram. Part 1 states calculate the energy used in converting 0.075 kg of boiling water to steam. So question is so Q is equal to M multiplied by LF, which is latent heat of vaporization. That's the latent heat of vaporization. Then we write mass, which is 0.075 multiplied by 2.25 multiplied by 10 to the power of 6. So the energy used in converting 0.075 of boiling water to steam is 170,000 joules. So this is the final answer that we have to write as energy in question part 1. Then part 2 states the hot plate operates at 240 watts 0.65 amps. Calculate the energy supplied to the hot plate in 20 minutes. So energy is equal to voltage times current times time. So the voltage is 240 multiplied by the current, which is 0.65 amps, multiplied by 1200 seconds, because 20 minutes we have to convert 20 minutes into seconds. So 20 multiplied by 60 is 1200 minutes, 1200 seconds. So multiplied by 1200, which is 190,000 joules. So the energy supplied to the hot plate in 20 minutes is 190,000 joules. Then part 3 states suggest why the answers to BI and BII are not the same, because some of the energy is transferred to the surroundings, which is air or atmosphere, because when the energy is transferred from the hot plate to the pan containing water, some of the energy, which is over here 20,000 joules of energy, is lost in the surrounding area, which is the air or the atmosphere. So this is what you will write in question part 3. Question 8a states draw a straight line from each quantity on the left hand side to a speed of the right on the right hand side, which is typically for that quantity. So the speed of sound in gas is 300 meters per second. So we'll put a line from speed of sound in gas to 300 meters per second. And the speed of sound in solid is 3000 meters per second. So we'll connect these both with the line. Then question B states explain why sound waves are described as longitudinal, because oscillation of particles of medium is parallel to the direction in which the waves are traveling. So this is what we will write in question B. Then question C states figure 8.1 shows how the displacement of the air molecules at an instant of time varies with distance along the path of a sound wave. So this is a displacement, and you will question part 1 states on figures 8.1 sketch which two cycles of the sound wave that has a shorter wavelength and a greater amplitude. So greater amplitude and a shorter wavelength. So we will move the wavelength a little bit onto the left side and draw a line from 0 over here, and then like this. It will be the wavelength will be shorter, and it will be at a higher distance, higher displacement as compared to the first wavelength. So this is how we will draw the wavelength, two cycles of the sound wave. Then part 2 states the two changes in the sound heard from this wave compared with the original wave. The two complete waves with greater amplitude the greater amplitude, and second is waves with higher frequency and higher volume. So over here, this we will write in two changes of the sound heard from this wave compared to the original wave. So the first one is two complete waves with greater amplitude, and the second one is waves with higher frequency and higher volume. So this is what we will write in part 2. Question 9 states in the circuit shown in figure 9.1, resistors can be connected between terminals P and Q. The EMF of the battery is 6.0 volts. So this is a circuit shown. Then question A states calculate the current shown by the ammeter when a 12 ohm resistor and a 4 ohm resistor are connected in series between P and Q. So over here first we'll calculate the current, which is I is equal to V divided by R, and 6 divided by R, 6 divided by 12 plus R, because over here we have two ammeters, two resistors over here, which is 12 ohms and 4 ohms. So 12 plus 4 is 16, so 6 divided by 16 is 0.38 amps. So the current is 0.38 amps, and we'll write amps over here. Then part 2 states connect in parallel between P and Q. So R is equal to 12 multiplied by 4 divided by 4 plus 12 is equal to 3, because 48 divided by 16 is 3. So I is equal to V divided by R. So 6 divided by 3 is 2 amps. So the current will be 2 amps, and 2A will be the final answer. Then question B states state a relationship between the resistance R and the length EF a wire of constant across sectional area. So we will state the resistance is directly proportional to the length. So this is what we will write in part 1 of question B. Then part 2 states the resistance R and the cross-sectional area A of a wire of constant length. So resistance is inversely proportional to cross-sectional area. So this is what we will write in part 2. Then question C states the 12 ohm and 4 ohm resistors in A are wires of the same length and are made of the same alloy. Calculate the ratio cross-sectional area of 12 ohm resistor divided by cross-sectional area of 4 ohm resistor. So over here ratio is equal to 4 divided by 12, which is 1 divided by 3. So the ratio is 1 to the ratio of 1 to the ratio of 3. So this is what we will write in question C. Question 10 states figure 10.1 shows a coil of wire rotating steadily in the magnetic field between the poles of a permanent magnet. The current generated in the coil is to pass through resistor R. So this is a coil with two magnets on the sides, and this is a resistor of C and D. The apparatus in figure number 1 is part of a AC generator. This what is connected between the ends A and B of the coil and the connection of C and D. So there will be two slip rings and brushes connecting on at the ends of A and B of the coil and the connections C and D. So there will be two slip rings and brushes. So this is what we will write in question A. Then question B states on figure 10.2 sketch a graph to show the variation with time the current through R. In part 2 states over here first we will draw a normal graph of the current from here, from the point 0 up till it's 0, then again to negative, then to 0, and then to the positive. Like this it will be in 2 repetitions. So like this we will draw. Then part 2 states show the t corresponding to 1 complete rotation of the coil. So this is a 1 complete rotation of the coil. So this is what we will show. Over here we will write T. Then part 3 states State two ways in which the graph would be different if the coil spins at a faster rate. So the time t decreases and the frequency increases, and second is the peak to peak current along y-axis increases. So this is what you will write in part 3. The question C states, suggest what could be connected between C and R so that the current in R is always in the same direction. We will write diode because it will stay in the same direction every time. So the diode will stay in the same direction. So we write diode as the final answer. Question 11a states, complete a table below for 3 types of radiation. Radiation is first is gamma. Nature it's electromagnetic radiation. Charge is 0 and it is stored by 5 centimeter of lead. Then second is beta. It's the nature of electron. The charge is negative and it is stopped by 1 millimeter of air, 1 meter of air. Then alpha is a nature of helium nucleus with a charge which is positive and it is stopped by a thick paper. Then question B states, an isotope of strontium is represented in nuclide notation as 9038 Sr. For neutral atom of this isotope, state the proton number, which will be 38 as stated over here. Then the nucleon number, which is 90 as stated over here. Then the number of neutrons, which will be 90 minus 38, which will be 52. And the number of neutrons will be 38. So this is a neutral atom of this isotope. Then question C states, a sample of radioactive material is placed near a radiation detector. A count rate of 4800 counts per second is detected from the sample. After 36 hours, the count rate has fallen to 600 counts per second. So calculate how many more hours must pass for the count rate to become 150 counts per second. So the half-life of 4800 counts per second is 2400 counts per second, then 1200 and then 600. So after 4800 we will write over here how many more hours will be needed for the count rate to become 150 counts. So after 36 hours it states the count rate has fallen to 600 counts per second. So at 600 counts per second the time is 0. Then at 300 it's 12 hours and then at 150 it's 24 hours. Why? Because after 36 hours 600 it has fallen to 600 counts per second, which is it has decreased 3 times. So this means we will divide 36 by 3, which will be 12. So after every 12 hours we have a half-life of 4800 counts, a half-life of this radiation detector, radioactive material. So for example, 4800 after 0 hours, 2400 after 12, then 1200 after 24 hours and 600 after 36 hours. Then we will continue from this point onwards, not from starting. So over here at 600 it's 0 example, and then 300 is 12, and at 150 it's 24. So right, number of hours is 24 hours. So this is what we will write in question C.